Welcome, physics students, to option E.1, first order social forces, under the option of life physics, which is kind of misleading because you only actually get one option. But anyway, we're going to be studying this, and you can study higher order social forces when you get to college, but it's beyond the IB. So, to get started, in the early 2000s, physicists thought there were only four fundamental forces, and these were electromagnetic force, the weak and strong nuclear, and gravity. Obviously, now we know there's more, but at the time, all the models seemed to work, and in experiments, it all worked, so we're done, right? So it turns out it's no, because there are social forces left out. And this all started with Benjamin Slayer performing the Dragon Sniper 69 experiment in 2013. So where he confirmed the effects that social interactions have on the laws of physics. And this was a huge deal. It was a huge paradigm shift because we realized that science was not completely parallel with everyday life. And the IB loves to ask about the significance of the Dragon Sniper 69 experiment. So, number one, it confirmed years of speculation about physics in social settings and how it was different. Two, it opened up a new realm of physics that's been studied for the last 5 or 6 years. And he was the first physicist to become cool and bring physics into a social mainstream setting. And we still thank him for that. So here's a definition for you for social forces. It's a class of fundamental forces that deal with physics in social situations. Specifically, we are studying first order social forces, where make sure you take note of the notation. Uh, Oftentimes, questions will use this notation, but it's a social force that operates on the basis of one perspective for both measurement and interference. And this is very, very, very important. Interference we'll talk about more in E.1, E.2, but measurement is what we're going to talk about a lot in this video. So before we begin, make sure you think about these questions. Like, on a bad day, do you realize how many unlucky things just seem to happen to you end on end continuously, um, even though they seem to have very low probability of happening? Like this man falling off his bike, or how time seems to fly when you're having fun. So these are all questions that life physics can answer for you, and we will answer in the next few videos. So first, we're going to study the force of love. Have you ever felt a force pulling you towards attractive people? Um, a lot of people have, but Joe Radog especially did, and he began investigating this force in 2012. He eventually plotted love force against distance and found an inverse square relationship. This should remind you of two other forces that we've learned. Hopefully you still remember them. He continued his research and found direct correlation between love force and appearance, which makes a lot of sense intuitively. And this helped him formulate his force of unconditional love, or F of L, or F love. If you can't draw the heart, you can always use L. It's a force experienced by two persons that's proportional to both persons' appearance and inversely proportional to the distance between them squared. And in your data booklet, this is how it looks like, uh, where f of love equals delta 1 over delta 2 over d squared all times eta, where eta is the emotional permeability of free space, about 69.6 times 10 to the power of 9 newtons per Beckham squared per meter squared. And appearance is measured in Beckham's, and d is measured in meters. So a few more important things about this force. The units for appearance were originally supposed to be radogs or RDs, but the science community at the time didn't really think he was suitable to be the candlestick for appearance, so they eventually stuck with Beckham's. Now, the measurements for appearance come from an external organization to eliminate biases, and here is a sample diagram, a sample table of some typical values. Most importantly, the one that you will all use in problem solving is this one for an average person. This comes from your SOCOS textbook. Delta can be both positive and negative. It's rarely negative, and so rare that in the IB we basically treat delta as greater than 0, but do know that it can be negative. Due to the inverse square proportion, the force of love will never equal 0, and you can verify this mathematically. That's very important. We'll talk about that more later. As long as delta 1 and delta 2 are of the same sign, force of love will always be positive, and you can also check this with the formula. So both these last two observations form Radog's law of unconditional love, where that's a law that states that love can always exist with the right intentions and conditions. And the IB loves to ask about this law, specifically the postulates of it. So here are the two postulates of this law. If both parties intend to engage, the force of love will always equal zero, will never equal zero at finite distances. And this is proven by the inverse square proportion. And secondly, everyone can experience a positive love force as long as both persons' appearance are of the same sign. We talked about this just now as well. I guarantee the IB will ask a question about the postulate, state two postulates of Radog's law of unconditional love. So here, take out your lecture examples and try example one before looking at my solutions. So, um, pretty straightforward. It's given the d is given, delta is given, and eta is given. We just find the work. Work is forced through a distance. So when we plug in the values, I got 2.9 times 2.9 megajoules per second, and that's quite a lot of energy to spend just for love. It's across the Earth. So the next phenomenon we're going to talk about is time acceleration. Have you ever heard the saying "time flies when you're having fun"? Excuse me. So for many years there was no way to really study it because it was a perception thing. But now, but eventually it was finally studied by Sang Transfer Ho in 2015 with in conjunction with neuroscience. And he's a very prominent life physicist. He's very famous for this discovery, where he discovered a quantifiable difference between perceived time and real time. Um, and this helped him develop the theory of perceived time acceleration in 2016, where this is how it shows up on your data booklet, which is a phenomena where perceived time changes in situations that involve enjoyment or dread, where F is enjoyment, or I like to remember it as fun. It is measured in net emotions per second. Alpha is the age of the individual. T of P is perceived time, and T naught is standard time. So in my experience, students usually find difficulty with this equation, so we're going to split it up and look at it individually. So if we look at the components, we can find that there's direct correlation between negative of enjoyment and the cube root of alpha with time acceleration. So case one, when enjoyment is greater than zero, so this is when there are more positive emotions than there are negative, then perceived time will decrease with respect to standard time. In case two, when f is less than zero, what that means that there's more negative emotions than positive, and that means that perceived time will increase because negative times negative is positive with respect to standard time. And finally, in case three, when f equals zero, when enjoyment is zero, and this is when enjoyment is zero, so there's the same amount of positive and negative emotions, then perceived time is not any different than to standard time. For this age variable, it's slightly easier. The older you are, the more perceived time will change with respect to standard time. And the younger you are, the less perceived time will change with respect to standard time. So these two correlations help us understand Ho's final conclusion in his report, which is basically the more fun and time you experience, the more different time is between your perception and the standard. So some more important things about time acceleration. If you think about it, if you think about using it for your favor, then it will not work. And this is still a mystery in our field, and we don't know why, but that's what happens in experiments. He became the first prominent, globally recognized physicist with a non-physics major. He studied environmental science. He transferred to environmental sciences in year 2 of college. And also, this is an approximation. Make sure to keep that in mind. Usually, it underestimates time acceleration. Third, it does not work well at higher ages, and we will see this in example 3 later on in the video. So before that though, first try this question on your own before looking at my answers. So, at his 15th birthday, Noah celebrated 2 times, laughed 5 times, but felt bored 9 times and cried 7 times from 1 to 2 p.m. Wow, jeez, what a birthday party. So calculate how long that time felt like to Noah. So first, we find the net emotions per hour. We just basically you subtract the negative emotions from positive emotions. We get -9 emotions per hour. You change the units to emotions per second because that's how F is measured. Make sure to remember that. And then I basically rearranged the left side of the equation for T of P by multiplying T naught and adding T naught. When you plug in all the numbers, you get about 1 hour and 40 seconds, which is only 40 seconds longer than the original time. That may shock you a little bit, but that might contribute to how it underestimates time acceleration. Try this question on your own. This is a very important question. So to understand this, first the question is deduce the maximum net emotions per second possible for a person age 92. So first we need to recognize that TP minus T naught over T naught is the percentage difference between TP and T naught. So this means that TP T naught must always be less than -1, and you can prove this mathematically to conserve time. But I will not do that here. I can maybe do that in class for you. So that means that for TP minus T naught to always be greater than, oh, this should be less than. Sorry, this should be less than -1. Then the left side of the equation will also be less than 1 if you take away the negative sign. It's the same here. So then if you rearrange for F, you get that F has to be less than 1 over alpha cube root 1.8. So you get about 0.128 net emotions per second. And so to put that in words, that is saying that a person age 92 can only experience about 7 net positive emotions per minute. And this may be one of the faults of this model. So the last thing, but this leads me to really well into the last topic, which is actually very importantly, there is no limit for perceived time there's no limit for net emotions in the negatives. You can go as negative as possible, and maybe I can show that mathematically for you in class. So this leads me very well into my last topic, which is the law of diminishing happiness. There's a law that dictates that the total happiness humans can experience decreases with time inversely. And this is shown in your daily locus by this equation right here. So this comes from ever since the 1900s, scientists noticed a global decline in happiness measurements. And you can see on the graph here, it goes very similar to a 1 over t graph. And we are right here at the cusp of a new measurement coming out. So all physicists will be trying to find out what is next for our happiness. In the 2000s, the scientists thought that it was due to overworking and increased technology use. But now we know, or I guess we think we know, that it's a law of nature. And now we'd say that just like entropy increases, happiness always decreases. But all in all, we have no idea why this is the case. There are some theories, like Nathan Smith, who's also deemed Cookies. He's a prominent life physicist. He said that the smartest systems are tasked with the most difficult problems. Humans are such systems that inevitably get crippled under their heightened responsibilities to the world. This is his opinion, and this is a very strong theory. It's the idea that although we are better at perceiving the world, there are more responsibilities and burdens that come with that, and that outpaces our ability to perceive happiness. But obviously, this is still a theory. If you guys want to get the next Nobel Prize, this is probably the best shot. You find out a physical explanation for the law of diminishing happiness. So let's finish this video with this last example question. So many say that their last years were their happiest ones. So I have here that according to the law of diminishing happiness, happiness decreases with time. This means at the end of people's lives, they will have the least happiness. This is one argument against that claim. But as the command term is discussed, we need to talk about both sides. So however, one can say that happiness decreases the least at the end of one's life. The difference in happiness across 4 years at youth, like from 6 to 10, or at the end is like from 96 to 100 years old, is drastically different, with the latter being much, much less. And you can check this mathematically. So in this sense, you can be the happiest at the end of one's life because you lose the least happiness relatively. And this is the type of question that IB will ask you about this.